I guess it's a really good resource for your teaching.
That's true.
I've already posted the first one online. I can send you the web link because you can change it.
And I can do commercials too. Okay. All right. As you know, every nucleus has a value of I associated with it. And it's a quantum number, and so it can only have certain allowed values. Okay, and for various reasons, they're listed in values of 1/2. So the simplest is, so they can be 0, 1/2, 1, all the way up here. Okay, so we can get a little table going here, where the nuclear spin is actually determined by the composition of the nucleus, which is not terribly surprising. And it's based on the number of protons and neutrons. We don't separate out the number of neutrons usually, but that's included in the mass number. Okay, so just by looking at the atomic number and the mass number of the nucleus, you can get a good idea of what its properties will be like in NMR. So if the mass number is even and the atomic number is even, the number of protons and neutrons will be even. Mathematically, that's the only way you can do that, and the spin will be 0. If I is 0, then it will not give a signal in the NMR. It will not have the net nuclear spin, so there's nothing for the magnetic field to interact with. And so these will be silent nuclei. If both the number of the protons and the neutrons are odd, then the spin will have integer values. And then if the mass number is odd, and the atomic number is any number, odd or even, that means we can have odd even or even odd. And that will give us values in atoms. Okay, so in kind of looking at all these different possibilities, there are kind of 3 main cases. One is where you have I equal to 0, the nucleus is silent, there's no magnetic moment. The very special case of I equal to 1/2, and that is where we do have a spin, but the nuclear charge, the positive charge in the nucleus, is spherically symmetrical. So there's no quadrupole moment in there. So the simplest case, of course, is hydrogen, which has a spin of 1/2, so there is a net spin, but there's only one proton, and so the distribution is spherical, of positive charge is spherical. Once you get more protons in there, you can have them arranged symmetrically and spherically, or you can have more protons in one direction than another, and that's what gives rise to the quadrupole. Okay. So we have these situations. Not having a quadrupole will be a very useful property for us. And then finally, if I is greater than 1/2, we have a non-spherical distribution of positive charge. That gives rise to the quadrupole. Okay. So, let's take a look at a few other kind of physical properties of the nucleus that come about as a result of the spin and the quadrupole. One very important number is called the magnetogyric ratio. So we'll have a magnetic moment. That magnetic moment is designated mu, and it's equal to gamma times P. Okay. And essentially, gamma is equal to 2 pi mu over h I. Okay, so mu is our magnetic moment. This is essentially, again, if you rearrange a little bit, P is obviously everything in here that is not mu. Okay. And so 2 pi over h is very familiar, h bar, the reciprocal of h bar. And we have our spin quantum number in there. Okay. So the ratio of the magnetic moment to our spin is just related by some constants. And that ratio is the gyromagnetic ratio. That is going to determine kind of our sensitivity of our nucleus to the NMR experiment. And it's all, again, kind of related to how well that can interact with the field. It'll ultimately go to the whether you get a strong signal from this nucleus for a certain size magnetic field in there. So some things really give it a nice strong signal, some things we can barely measure. So I think now is a good time to go and take a look at the chart. Do you have your books with you? No, okay. make a note in your books are two charts of nuclear properties on page 322. Okay. In table 1, they have all the nuclei with spins of 1/2. And so these are going to be the ones without the quadrupole. These are going to be the easiest to use in samples. Now, you're all familiar with hydrogen, which has an abundance of about 99%. So it's everywhere, it's in compound, it's chemically interesting, that's why that works. As you know with carbon, carbon-12, would carbon-12 have a nucleus? Would you be able to see carbon-12 under any conditions? Right, because from the table, 6 protons and 6 neutrons, so they're both even, and so I is 0. So there is no chance of seeing carbon-12 in the NMR. Carbon-13, of course, has very low abundance, but it has a spin of 1/2. It's a pretty reasonable nucleus to study here. So I will put up a few of these. We have to concentrate on a couple of things. Number one is you have to have some natural abundance in there. If you have it, you know, if it's only 1 atom in a million, you know, you're probably not going to see it in your sample. It will be so dilute. And so you would have to enrich your sample, which means getting a very expensive exotic nucleus and chemically incorporating it in there. Or you're going to have to really crank up the power in order to see these tiny amounts. So let me kind of do a table here. All split 1/2 nuclei. Just do gamma. And let it go at that. Let's do one last column here. We'll get into some of these specific definitions later. Right now, relative receptivity is just comparing it to carbon-13 in this table. So the ability to see a nucleus on this scale is carbon-13 is 1. Anything greater than that is better. Anything smaller than that is worse. And so hydrogen comes in at a natural abundance of 99.9%. I believe it holds the record for the largest magnetogyric ratio. And it's compared to carbon-13. Is nearly 6,000 times more receptive or easier to see in the NMR than carbon-13. Okay, by way of comparison, C13 has an abundance of about 1%. Its magnetogyric ratio is 6.73, and of course is a receptivity of 1. So these are the two that you're familiar with. We'll take a look at a few other nuclei. One really good one that's just about as good as hydrogen is fluorine. And you can do a lot of things chemically with fluorine, and this is why people use it as a labeling agent in a lot of biological molecules, because if they can replace hydrogen with a fluorine, that tag goes along. You can look at the NMR and spot it and pretty much do everything that you did with hydrogen. Fluorine 19 has 100% abundance. Every fluorine in nature is a fluorine 19. Its magnetogyric ratio is 25.18, virtually the same as hydrogen. And so it's not surprising that its receptivity is also about the same as hydrogen. So pretty much everything you know about hydrogen can probably equally be applied to fluorine. Another nucleus that gets used quite a bit is phosphorus. Again, a biologically important element, although it's usually just in there as phosphate, but there's a lot of inorganic chemistry with phosphorus. Again, 100% abundance. Not a bad value for gamma. So again, not quite as good as hydrogen and fluorine, but still excellent properties for NMR. Now, from here on out, we kind of run into problems here. These are the big three, the best nuclei. Well, let's put in one more. Thallium-205 has a natural abundance of about 70%. Gamma of 15.69, very good. And this translates into a receptivity in there. From here on out, everything is going to be worse. Now, there are some elements that we do a lot of chemistry with, and we're kind of interested in. So let's kind of draw a line here and look at what happens with that. We have silicon. Silicon 29 has a natural abundance of about 4.5%. Okay, not terribly abundant, but better than carbon-13. Okay. Its value for gamma is actually a negative 5.32. So gamma can have positive and negative values. I assume it's associated with the value for the magnetic moment. Okay, I'm not sure how that comes in there. And what's our last one? Okay. So its receptivity is just 2.16. So twice that of carbon-13, but again, you can see the problems are developing here. Value of gamma, kind of comparable, but opposite in sign here. Abundance, a little bit better. Okay, so you can kind of see by comparison. Silicon about the same as carbon. Other useful ones, there aren't that many. One would think that you might be able to do things, rhodium. Okay, people do rhodium NMR. Organometallic chemists do. Rhodium 103 its natural abundance is 100%. So far, so good. Its gyromagnetic ratio is less than 1. Okay? And so that's what kind of gets it, its receptivity. It's only about 1/5 that of carbon 13. So I won't go ahead and reproduce the whole table. When you're looking at it, now there are nuclei that people look at, but some of these are just not chemically that interesting.